Hello students, your physics teacher Hassan Darwish with you. In this video, in fact this is video 4 about chapter 4, mechanical oscillations. I'm going to explain the oscillation of a torsion pendulum. First, what is a torsion pendulum? Okay, let's see the torsion pendulum. Here in reality, let's see this video, small or short video. So the torsion pendulum in reality consists of a vertical torsion wire, as you see, and a body. Here is a metal disc suspended from the lower end. Now here, look at the vertical wire. We fix it to a pivot point here, and the body is suspended. Clear? We choose this point as a reference point here. This spin is chosen as a reference point. Now we give a small twist, means we turn the body in the horizontal plane about the vertical axis, which is the wire, so that the wire is twisted. Now you see what happens? The body oscillates in the horizontal plane about the vertical axis. Okay? So this is a torsion pendulum. So it consists of a metallic wire O', as we've seen, one end of which is fixed to a support here, O, and a body is welded to the lower end. This is the body. Okay? So here is the equilibrium position of the body. Means the wire, when the body is in this position, the wire is not twisted. Clear? The wire is relaxed. Then theta equal to 0. Now when the body is turned by an angle theta, as you see, you turn the body, then the wire is twisted. The wire is twisted by the same angle here, angle theta. The wire thus exerts a restoring couple in the same way as the spring exerts a restoring force when it is compressed or elongated. We call it torsion couple. Here it is. Okay, which is proportional to theta. In the same way, Hooke's law for a spring. T in algebraic value equal minus kx in algebraic value. Okay? C is called torsion constant. Like the spring here, we call it stiffness or spring constant. Experimentally, C is proportional to the diameter power 4 of the wire and to the length, inversely proportional to the length. Now what is alpha? Alpha is a constant depending on the nature of the material. Means whether the material is iron, nickel, brass, copper, or mixture. I mean alloy. So D is the diameter of the wire and L is its length. In this case, when the wire is twisted by a certain angle theta, it stores elastic potential energy, which is half c theta squared. Okay? Now shift the body in the horizontal plane by a certain maximum value, theta m, as we did in the case of the elastic spring when we displaced the body by a certain distance xm and then released without velocity. Now what is the objective? The objective is to determine the differential equation that describes the motion of the body, its time equation, and the proper period. The same way as we did in the case of the horizontal elastic pendulum. Let's do this. Okay. Sorry. At any instant, let's use the black color. At any instant t, you know that mechanical energy of the system, which is the pendulum here, is equal to the kinetic energy plus gravitational potential energy plus elastic potential energy. You know this, right? Now let's go back to our pendulum. Here is the pendulum. Let's choose the level of the body as a gravitational potential energy reference. Okay, here. So GPE becomes 0. Okay? So GPE becomes 0. And don't forget that this body, I mean the oscillator here, is a rigid body in rotation. So what is its kinetic energy? Yes, it's half I theta prime squared plus, now the elastic potential energy stored in the wire, which is half c theta squared, where c is the stiffness of the wire or constant. Clear? Now here we neglected any type of friction. We neglect, in the ideal case, we neglect any type of friction. What does this mean? Mechanical energy is conserved, right? Conserved means it is constant. Means mechanical energy equal constant. So what's the derivative of the constant? Derivative of mechanical energy, always derivative with respect to time, okay? Equal to 0. d over dt means prime, derivative with respect to time, equal to 0. Let's do the derivative here. Half I, which is a constant. Now what's the derivative of theta prime squared? It's the same as u squared in mathematics. Derivative of u squared in mathematics, 2u u prime. So here, derivative of theta prime, 2 theta prime, theta double prime, plus half c, derivative of theta squared, 2 theta times theta prime, equal to 0. So theta prime different from 0, and rearranging this equation, we get the following. Theta double prime plus c over I, this is the constant, clear, times theta equal to 0. What is this? Theta is the function, clear, because theta varies with time. And theta double prime is the second derivative of this function. So this is what? This is a second order differential equation. Second order differential equation of the form. You remember the second video. Y double prime plus omega 0 squared y equal to 0 when we studied the mathematical note differential equation, where omega 0 squared here is c over I. Here I'm comparing this equation with the mathematical equation, the second derivative. Okay? Provided that omega 0 squared equal c over I implies omega 0, which is the angular frequency, is equal c over I. So I can find the proper period or the natural period. Proper or natural period is what? T0 equal, as we know, 2 pi over omega 0. And then you get 2 pi radical I over C. It's not necessary here to write I0. I enough. Don't forget that I represent the moment of inertia of the system. Be careful. Clear? I, moment of inertia. Clear? Of the rigid body, which may consist of a disk, a rod plus particle, etc., rod plus disk, etc. So moment of inertia of the rigid body or system. Clear? And C is the constant of the wire. So what is the motion here? Motion, as you see, is simple harmonic motion. This is the nature of motion. Clear? Why? Because the differential equation is of the form y double prime plus omega 0 squared y equal to 0. And what is the solution of this equation? Solution, which is always given. Clear? Theta equal in the same way as elastic pendulum, the same way, but this is angular motion. Theta equal theta m, sine or cosine, it doesn't matter for us. Cosine omega 0 t plus phi. Clear? Where, as we did with elastic pendulum, the first pendulum, theta m represent here constant of integration in mathematics, but here represent the amplitude. Clear? Amplitude of oscillation, and phi is the initial phase. It is the state of the pendulum at t equal to 0. Okay? Good. Let's do this example, direct application. Sorry. Here it is. This is the example. The body is a disk here of mass 20 gram and radius 10 centimeter. The torsion constant is this. At equal to 0, the disk passes through its equilibrium position with this speed. Determine theta. Okay? So theta equal theta m cosine omega 0 t plus phi. You know omega 0 radical c over I. C is given here, but we need I. I is half mr squared, 10 to the power minus 4. So you calculate omega 0. Now we need theta m and phi. Clear? We apply the initial condition. We only determine theta m and phi by applying the initial condition. Here, theta 0 equal to 0, since the body passes where? In the equilibrium position. And the initial speed is theta prime 0 minus 3.2. Now try to do the calculation as we did in the first video. We get pi equal pi over 2 or minus phi